Hey all dear friends, welcome to the Quantum Guru. Today I've come up with a very good question of electrostatics from Pathfinder. It's a build up your understanding question number 29. So as you can see in your screen, the question states charge distribution on a rod bent as a semicircular arc of radius r follows a function lambda is equal to lambda naught sine theta. Here lambda is the linear charge density at a point on the rod at an angular position theta as shown. Lambda naught is a positive constant and theta is the angular position of the point as shown in the figure. Find the ratio of the electrostatic potential at the center and at a general point on the diameter AB at a distance small r are smaller than capital R equal to R from the center. So what we have to do, we have to find the potential at the center on this diameter and potential at any other general point at a distance small r from the center on the diameter. So basically I'll attempt to find potential at a general point on the diameter, and from there if I put r is equal to 0 I will get the potential at the center also. So let's go ahead. So here is a non-uniformly charged ring of radius r. Linear charge density at angular position theta is lambda naught sine theta. So I want to take an element of the ring between angular position theta to theta plus d theta like this. This is at angular position theta, and then I'm taking element between theta to theta plus d theta. So width of this element is r d theta. So the charge of this element will be lambda into length. That length is r d theta, and lambda is lambda naught sine theta. Now let me take a general point P here on the diameter. Suppose this is a P, and this point is at say distance r from the center, and suppose this point P is at a distance say r dash from the element chosen. So because of this little elemental charge dq, potential at the point P will be given by dv is equal to, that is a point charge, dq, so k dq divided by r dash, and in place of dq I will write lambda r d theta, and lambda is lambda naught sine theta. So put the value of lambda and then dq is equal to lambda r theta, so that will be k lambda naught r sine theta d theta, and the r dash. R dash you can write using the cosine rule. So this is r, this is small r, this is theta, and this r dash. So r dash is the square root of r square plus small r square minus 2 capital R small r into cos theta. So that is this. Capital R square plus small r square minus 2 capital R small r cos theta. The integration is a very straightforward thing. You can see that the only variable here is theta. In this, capital R is fixed, small r is a fixed point where I want to find the potential. The only thing is small theta. So, and as my element goes from here to here, so theta will go from 0 to pi. To calculate this integration, I will have to take some substitution. So I am taking a substitution as a t is equal to whatever is in the denominator. T I am taking a square root of capital R square plus small r square minus 2 capital R small r cos theta. One thing I want to do right now, I will have to change limit. So here as theta is going from 0 to pi, how the t is changing. So when theta is at the lower limit at 0, if I put it here 0, so cos 0 is 1, so that will be square root of capital R square plus small r square minus 2 capital R small r square root, and that will be square root of capital R minus small r whole square, that is simply capital R minus small r. So the at theta 1 is equal to 0, the t will be capital R minus small r. And when the theta will take its upper limit, that is a pi, so theta 2 will be how much? Here cos pi will be minus 1, so minus minus plus 1, so that is a capital R square plus small r square plus 2 capital R into smaller, that is a capital R plus small r whole square, and then there is a square root, so that thing will become basically capital R plus small r. So at the upper limit of theta, the t will become capital R plus small r, that's it. So now just take a differential of that t, so dt is equal to the take the differential, so we'll have to differentiate that thing, so that whole thing will be square root of r square plus small r square minus 2 capital R small r into cos theta, and go inside the square root and differentiate. This is a constant, this is a constant, this is a constant, this is only cos theta is variable, so derivative of this term minus 2 capital R small r cos theta is equal to 2 capital R small r sin theta, and then there should be t theta. And see, here in place of sin theta, r is also there in place of this capital R sin theta d theta, and that whole thing from here. One more thing, here 2 will come, so that 2 and that 2 will get cancelled. So in place of this thing here, and that is here, and here that is a small r, so what you can do, you just multiply small r and one small r here, so that whole thing can be substituted with dt. So I just want to erase this. So now I can write dv is equal to k lambda naught by r and dt, simple. So integrate this to get v, so v is equal to integration of dv, so that integration is k lambda naught by r, this is a constant, and then there is a dt, and the limit of t as theta goes from 0 to pi, t will go from t1 to t2, and integrate it to get k lambda naught by r t2 minus t1, and see what is t2 minus t1, this is t2 capital R plus small r, t1 capital R minus small r, the difference is 2 small r, so we will get k lambda naught by small r into 2r. So that is a very unexpected result. This is independent of r. So the potential that I've got is 2k lambda naught. So it means the potential that I've got, let me go to the next page, here at any general point P, here this is at a distance r, lambda was lambda naught sin theta, this is coming, if the lambda is lambda naught sin theta, it will not come for any lambda, so potential at that position r, I've got 2k lambda naught. It means it is 1 over 2 pi epsilon naught lambda naught, that's it, or lambda naught by this. So it is a constant. So it is a constant, mean the ratio of the potential between center to any general point is 1, because the potential is same everywhere. And what does this actual mean? It means that if I go from here to here to here to here to here, here, potential is same, and the potential is not changing. So if I go from here to here along this path dr, displacement, so potential is not changing, it means dv is equal to 0, and I know that dv is equal to minus E dot dr. And one thing is clear, that because of all these charges, the electric field would be in this plane only if the charges are positive in the away direction. So because from here to here dv is 0, so E has to be perpendicular to dr. So dv is 0, so E is perpendicular to dr. So one very important interpretation of this result, that at all these points electric field is going to be like this. I cannot comment upon the magnitude of that E, but I can certainly comment that the electric field at all the points on the diameter is going to be perpendicular to diameter, and that's a very good result, and that enables us to make some question on the work energy theorem. If I can make a question like, suppose an external agent takes some charge from some point on the diameter from here to here, slowly, what is work done by that? So answer will be 0, because there is no change in potential. So there is no change in potential energy. So that's a very good question. Hope you like this video. Enjoy physics. Stay tuned for the next upcoming video. Thank you.